This is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic will be substitution in multiple integrals. Okay, so we saw substitution in single integrals back in Calc 1 or Calc 2. The same idea applies here as far as goal. So the goal of substitution is to replace hard integrals with easier ones, and that might involve replacing the integrand or the limits of integration or both. Okay? And we've already seen this twice, so we've seen this twice already. We saw it once with double integrals when we had polar coordinates, so we had double integrals in polar coordinates. All right, so we had some kind of circular region in the xy plane. We replaced xy with r and theta. And we also saw it with triple integrals in cylindrical and spherical coordinates. All right, so we had some kind of cylindrical shape or a spherical shape. We replaced x, y, z with either r, theta, and z, or rho, phi, and theta. Okay? All right, so how does this work in general? Well, we're going to start with some kind of region in the xy plane. So we start with a function f of xy and a region R in the xy plane. So we're going to start with functions of two variables and talk about double integrals, and we'll talk about triple integrals briefly at the end. Okay? So you have this function f of xy in a region, and our goal is we're going to transform R into a region G in the UV plane by applying the following transformations to xy. So we have a region G in the UV plane, and x will be some function g of uv, and y will be some other function h of uv, right? So we have some transformation of x and y based upon a function of u and v, okay? So what that means is that here's a region R, so that's R, and there's a point x and y, and this is in the xy plane, right? Then we're going to apply the transformation, so we apply x equals g of uv, we apply y equals h of uv, right? And then what do we get at the end of this? Well, we've applied our transformation. We get some new region. Now this is the UV plane, right? This is the region G, and this is some point UV where xy is sent to some new point UV, right? So xy is mapped into some point UV, and the entire region R in the blue is mapped to the entire region G in the black by the green transformation, okay? So that's the goal of substitution. Well, what do the integrals look like is the question. So we used to have some double integral over R of f of xy dx dy, and this might have really been dy dx, doesn't make a difference. And then this becomes some double integral over the region G, where we're composing f with g and h, all right? So now we have f of g of uv and h of uv, right? Because this is x and that's y, okay? And then here comes the part that's new. We also have it times the absolute value of this j function of u and v. So we have it times the absolute value of this j function uv du dv. And so the question is, well, what is this j function, right? Well, the j function where j of uv is called the Jacobian determinant. So it's called the Jacobian determinant. And notice it's a determinant. That's not just a word for any old use. It means what we have here is a determinant. We're taking the absolute value of a determinant, Jacobian determinant, of the transformation x equals g of uv and y equals h of uv. So with each transformation, there's associated a unique Jacobian determinant, okay? So what is it? Well, j of uv is defined as the following determinant. It's partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v, right? And then that gives you out, if you actually do that out, you get partial x, partial u, partial y, partial v, minus partial x, partial v, partial y, partial u, right? Okay. So this is the Jacobian determinant. Okay. All right, let's try this out and see how it works on an example we've already seen. So we have our formula. All right. Let's see whether or not this works for polar coordinates. So for example, I said already that we've already seen a substitution method by transforming rectangular coordinates to polar coordinates, right? And we had to go through that lengthy process of looking at polar rectangles and taking limits and whatnot. Well, now that we have this formula, let's see if it's any easier to get that. So I want to convert from rectangular coordinates to polar coordinates, right? So in this case, my u and v, I'm going to polar coordinates, right? So in this case, u and v are the variables r and theta, right? And the transformation we know is x equals r cosine theta and y equals r sine theta, right? So both x and r, or both x and y, excuse me, are defined as functions of r and theta. Okay, well, what's the Jacobian determinant here? Well, we need partial x, partial r, partial y, partial r, partial x, partial theta, partial y, partial theta. All right, that's determinant. And so what are these things? Well, partial x, partial r is just cosine theta. Partial y, partial r is just sine theta. Partial x, partial theta is negative r sine theta. Partial y, partial theta is r cosine theta, right? And so multiply these out, you get r cosine squared theta minus negative r sine squared theta, which is plus r sine squared theta, which is equal to just r. That's 1, right? Okay. As a consequence, the double integral over some rectangular region, f of xy dx dy, so r is some region in the xy plane in rectangular coordinates becomes double integral over some region G of f of r cosine theta, r sine theta, right? This is how we did polar coordinates before. We just plugged these in for x and y. And then we had times the absolute value of r, dr d theta. Well, this is exactly g f r cosine theta r sine theta times r dr d theta, as long as r is greater than or equal to 0. And this is a very familiar formula to us, so this is a familiar formula to us, right? This is just the formula we used for polar coordinate integration, right? And notice over here, as long as r is bigger than or equal to theta, so remember, r is a directed distance. R is a directed distance, so r could technically be less than 0 also. So this thing works out, right? The Jacobian got us the proper formula for polar coordinates. Okay, so let's try an example with an actual function here. We've seen that one does work here to give us a familiar formula. So that's gone. Okay. So let's evaluate the integral 0, 4, x equals y over 2, x equals y over 2 plus 1, right, of the function 2x minus y over 2 dx dy. Okay, let's do that. And then let's use the transformation, so using the transformation u equals 2x minus y over 2, and we'll use v equals y over 2. And for all the problems you're likely to see, you'll probably be given a transformation already. Sometimes the hardest part is finding the proper transformation to make these things work out. But it seems like this seems pretty natural to us. I mean, the big chunks of our function have become x and y, or u and v, and so this does not seem like a particularly abnormal transformation here. It seems to fit pretty well with what we have up here already. Okay, and then we will integrate over a region in the uv plane. Okay. Well, let's start by looking at what the region looks like in the xy plane. So the region R in the xy plane, well, we're integrating with respect to x first and y second. So y is just caught between 0 and 4, right? 0 and 4. And x is bounded between two functions of y. So x is bounded between y over 2 and y over 2 plus 1. Well, let's go ahead and, so let's write down x is bounded by two functions of y. Okay. Let's convert those to a more recognizable form. So if we look at that, well, x equals y over 2, right? That just means y equals 2x. And x equals y over 2 plus 1, right? That means that we have what? 2x equals y plus 2, so y equals 2x minus 2 is the other bounding curve here, right? The other bounding curve. So if I draw my region, so there's x, there's y, we know that y is between 0 and 4, and we know that x is between these two curves, or these two lines on this plane. So y equals 2x maybe looks something like that, right? y equals 2x minus 2, right? Well, that has x-intercept equal to positive 1, right? Because when you set x equal to 1, y is 0. So it starts over here, so this is like 1 for x, and then it extends parallel. That's parallel, right? So we have this sort of slanted rectangle looking shape here, right? Where this is the plane y equals 4 up here, so let's put that in. There's y equals 4. Down here is y equals 0. On the right side is y equals 2x minus 2. And on the left side is y equals 2x, right? That's the region R in the xy plane, bounded by those 4 sides, okay? All right, so now our goal is we have this region. We need 2 things. We need a corresponding UV region and a Jacobian. Right? We need a corresponding UV region and the Jacobian. Okay? So let's get those things. So let me erase everything down here. I'll leave up the R region at this point. Well, to get the UV region, our plan is we're going to take each of these bounding sides of the R region, convert them to U and V coordinates, and then find the boundaries of the new UV region. Okay? So that means that we need to convert y and x to U and V. All right? So if V equals y over 2, that tells us right away that y is equal to 2V. All right? So there's y in terms of U and V. Okay? And if U equals 2x minus y over 2, that tells us 2u equals 2x, and y is equal to 2v, so we can just go ahead and plug in a minus 2v, and that tells us that what, 2u minus 2v, or plus 2v, equals 2x, right? And then we can divide by 2, and we'll get x equals u plus v. So there are x and y in terms of u and v, okay? And now plug these expressions into the boundary curves for R, right? Now plug these expressions into the boundary curves for R. So let's see here. What do I want to cut out? So we have that. We have this. Let me go ahead and erase this whole thing up here to make room for a chart. So let's make 2 columns here for our chart. The first column will be a representation of the boundary of R in terms of x and y. So on the left side of the chart, I'm going to have the xy equations for the boundary of region R, right? So x equals y over 2. I could write it as y equals 2x, but I mean, there's no reason not to write it like this. Either way, it works fine. So I'll just put in terms directly of the integration limits. And x equals y over 2 plus 1, and y equals 0, and y equals 4. So remember, these first 2 were exactly the same as y equals 2x and y equals 2x minus 2. Writing them either way won't make a difference in your answer. Okay? So there's the boundary of R. Now let's write down UV equations for the boundary of our new region G. Right? So I want to take each one of these bounding pieces of R and form a new boundary piece of G. Okay? Well, x is u plus v, y is 2v, so we just plug straight in, right? We get u plus v equals v, right? That means subtract v from both sides. That just leads to u equals 0, right? So u plus v equals v means u equals 0, okay? Let's see, down here we get u plus v equals 2v over 2 plus 1. That's saying u plus v equals v plus 1, Well, that means u equals 1, all right? Okay, so these more complicated lines over here have become very, very simple boundaries in the UV plane, okay? Y equals 0 means 2v equals 0, which implies v equals 0, okay? And y equals 4 is 2v equals 4, which implies that v equals 2, okay? So those are our boundary curves for our region G, and so if we draw this out now, there's v, there's u. What used to be a slanted rectangle in the xy plane now becomes a straight rectangle in the G plane, or the UV plane, excuse me. So u goes from 0 to 1, v goes from 0 to 2. I kind of missed my mark there, but you get the point. So, and then there's the region G, right? So simpler looking than the region R. Okay? And this is just 0 less than or equal to u less than or equal to 1, and 0 less than or equal to v less than or equal to 2. Okay? So there's our region G. Now we need our Jacobian. So let me get rid of the chart. So the Jacobian is partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v. And remember that x is u plus v and y is 2v. Okay? So partial x, partial u is just 1. Partial y, partial u is 0. Partial x, partial v is 1. Partial y, partial v is 2. Right? So that's 1 times 2 minus 0 is equal to 2. Okay? So now we are finally ready to evaluate the integral. So our question originally was, do this using this transformation. Well, we started off with an integral in xy coordinates, 0 to 4, y over 2 to y over 2 plus 1. And our function was 2x minus y over 2, dx dy. Well, now, this is going, so the v limits are 0 to 2. The u limits are 0 to 1. Oops, not 0 to 0, 0 to 1. The function, well, remember, our original transformation was let u equal this. So this piece is u, right? In other words, our original transformation was let u equal to this thing, let v equal to y over 2. So this is u, right, times the absolute value of the Jacobian, du dv, like that, right? Okay. So that's 0 to 2, 0 to 1. Absolute value of 2 is 2, so this is just 2u du dv. Okay. Integrating with respect to u first, we get u squared from 0 to 1 dv. Okay. Plug that in. That's integral of 0 to 2. This is just 1, right? This is just 1 dv, so just looks like that. And this is v from 0 to 2, which is just 2. Okay? So our whole process was we went through, we transformed the region R to the region G, right? We found the corresponding limits of integration, which we have down here. We had a function that was much simpler, what we started with, u versus this 2x minus y over 2 deal. Found the Jacobian determinant, put that in, integrated. Okay, so let's try another one. Let's see, so let me get rid of everything up here. And again, as long as the transformation is given to you, things aren't so bad usually. Sometimes the hardest part, again, is finding the proper transformation that's going to work, and some integrals just don't really lend themselves to this. I mean, just like when we had substitution in single integrals, it didn't always work for every integral. The same idea applies here. Some integrals are still too hard. There's no nice transformation to make life easier on us. Okay. So, evaluate integral from 0 to 1 and from 0 to 1 minus x of square root x plus y times y minus 2x squared dy dx. Okay, so there's the integral. And then let's have our transformation be u equal to x plus y and v equal to y minus 2x. Okay, so there's the integral. There's the transformation that we want to use. All right, well, let's start. Let me start actually over here. So we want the region R in the xy plane. Well, so this is with respect to y first and respect to x second. So x is just bounded between 0 and 1. Right? Y is bounded between 0 and 1 minus x. Right? So again here, not again, but in this case, y bounded by 2 functions of x. Right? Okay, so when I draw this thing out, there's y, there's x. So x is stuck between 0 and 1. Y is stuck between 0 and the line y equals 1 minus x, which has y-intercept equal to 1. Well, so that right triangular region is our region R in the xy plane, right? Because here's the x limits. The y limits are between 0 and this line, 1 minus x. Okay? So there's R. Now let's find the corresponding region G in the UV plane. Okay. Well, this time things aren't quite so simple. They're still not too bad, but we're given the transformation u equals x plus y and v equals y minus 2x. So to solve for x and y in terms of u and v, we have to solve this little linear system, right? So if we multiply the top row through by a negative y, right? In fact, I'll even write this so it lines up the variables, so we can write this as negative 2x plus y, like that, right? So multiply the top row through by a negative 1. That makes a negative y here and a positive y here. So when we add the two rows, the y's will cancel. So we'll get what, negative u plus v equals negative x plus negative 2x is a negative 3x. Okay. And then divide everything by negative 3. We get x equals 1/3 u minus 1/3 v. Oops, didn't box the whole thing in there. So, all right, there's our x expression, right? Now let's just plug that back into either one of these guys and we'll get the y expression. We can plug it into the first one, for example. So u equals 1/3 u minus 1/3 v plus y. Right, so I'm plugging in x to the first expression here to get y isolated. Right. Let's see. This is 2/3 u plus 1/3 v equals y. Right. So there's the expressions for x and y. Okay. All right. So now we're going to make our chart. So let's see, do I want to cut anything out yet? Not really. Let me try to make it down here. So we'll make our chart. Again, we'll have XY equations for the boundary of R, and then on the other side, we'll have UV equations for the boundary of G. Okay? So this time our X and Y region is bounded by three different curves. It's bounded by this part of the Y-axis, this part of the X-axis, and this line. So our bounding curves are Y equals 0, X equals 0, and Y equals 1 minus X, right? Okay? And so let's see here. Y equals 0 means that we have 2/3 U plus 1/3 V equals 0. All right? Know what I have here? Yeah, that is, right? And so if we move the 1/3 V to the other side, multiply by 3, we get 2U equals negative V, right? So move the 1/3 V over, multiply by 3, get this expression. X equals 0 means that 1/3 U minus 1/3 V is equal to 0. Move the 1/3 over, right? That implies that we have U equals V, right? Okay. And then Y equals 1 minus X is 2/3 U plus 1/3 V equals 1 minus 1/3 U minus 1/3 V. Okay? So if that's the case, oops, wait, no. This should be a plus 1/3 V because it's a minus a 1/3. Yes, that should be plus 1/3 V. That looks right. So that means the V's will cancel. Add this over. The implication is U equals 1. Implication is U equals 1. Okay? So let me erase the region in the XY plane. And now let's draw the region in the UV plane. So now we're going to draw the region G in the UV plane, right? So what do we have? Well, we have 0 is less than or equal to U is less than or equal to 1, right? And V is bounded between negative 2U is less than or equal to V is less than or equal to U, right? So V is bounded between two functions of U. Well, actually, I don't want to put this up here yet, so let's not write this yet. Hold on, wait. Let's draw it first, and then we'll see what's going on. So that's going to work better. Yeah. All right. So here's the U plane. Here's the V plane. Here's 1, right? So this thing is bounded by U equals 1, right? Like that. And then U equals V, right, is going to be that line. So U equals V is going to hit that plane right there. That's the point 1, 1, right? So that's one boundary area of the curve, right? 2U equals negative V is the same as V equals negative 2U. So that's going to come down, let's see here. So more steeply, something like that maybe, right? Something like that. So this is the point 1 comma negative 2, right? And this triangular region is our G, okay? So I began with this idea, but it had to be one bounding curve as U equals 1. And then I saw where my other two curves intersected this bounding curve here. So this is V equals U, and this is V equals negative 2U, right? So this triangular region, and this is, of course, 0, 0, is the region G, okay? And then from this picture, we can read off the limits of integration here, okay? So now we see that U is bounded between 0 and 1, right? And we also see that V is bounded between negative 2u and u, right? So remember, the idea is these curves must intersect in some closed region. So they intersect here at 0, 0, and they cross at 1, 1, and 1, negative 2 here. That's what gives us these boundaries of integration for this problem. So the picture comes first, then the boundaries are read off that. Okay? All right. And let's see here. So now we can look at the Jacobian. So we have our region. That's half of our battle here. We need our Jacobian also. So let me get rid of all this stuff. So we need the Jacobian. And it's partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v. All right. Did I erase my transformations? I think I did. So where is it up here? X is equal to 1/3 u minus 1/3 v, and y is equal to 2/3 u plus 1/3 v. Right? So partial x, partial u in this case is 1/3. Partial y, partial u is 2/3. Partial x, partial v is negative 1/3. Partial y, partial v is positive 1/3. Right? So that's 1/9 minus a negative 2/9, which is a positive 3/9, which is a positive 1/3. Okay? So let's integrate now. So we've started off with 0, 1, 0, 1 minus x of a pretty ugly function, y minus 2x squared dy dx. Right? We converted to limits of integration in the uv plane. So we're going to put the u limits first and the v limits second. Remember, v is bounded by two functions of u, so we want to integrate with respect to v first to just get u's in there. So we'll put the v limits of integration. They'll happen first. Our function now becomes, well, square root u, all right, times v squared. Well, that's written as u to the 1/2 v squared, right, times the absolute value of the Jacobian, right, which is 1/3, and that's going to be dv du, all right? So v first, then u. Okay? So that's what I've got here, yeah. Let's see, do I want to kick the 1/3 out? No, I don't actually. So with respect to v first, this is 1/3 v squared, right? So the integral is going to be just v cubed, and the u 1/2 comes along for the ride. So we have u to the 1/2 v cubed evaluated from negative 2u to u du, right? So this is like a constant, and this is 1/3 v squared. Integral of that is v cubed. Okay. Let's see. So you plug in here, and u cubed times u to the 1/2 is u to the 7/2. So we have what? U to the 7/2. And then, let's see, negative 2u cubed is negative 8u cubed times u to the 1/2. So that's a plus 8u to the 7/2, because it's a minus a negative 8, right? Du, right? So that's integral from 0 to 1 of 9u to the 7/2 du. Okay. So integrate there, multiply by a 2/9, right, to get 2u to the 9/2, right? 2u to the 9/2 would give you that from 0 to 1. And let's see here. You plugged in 1, and you just get 2 here? Yeah. All right. That looks good. So there's the integral. So again, slightly harder this time because our region in the UV plane was slightly more complicated. But if we drew it out, okay, and we saw where the curves intersected, we could just read off the limits of integration from there. All right, so the last thing I want to mention here is that there is a way to do this in the three-variable case, and it's not even particularly surprising given our definition for the two-variable case, but it does lead to some awfully heavy algebra quickly, and so we're not going to do an example, but I'm going to point out that it does exist and that it's out there, and if you want to convince yourself, you can certainly try it on, say, for example, cylindrical coordinates and check and make sure it gives you the right formula. So there's also a substitution method for triple integrals. All right. And it says the following. It says if x, y, z is a function defined on a region D in typical XYZ space, right, then we can transform D into some region G in UVW space by using the following sequence of transformations. Well, x is just some function g of UVW. Y is some function h UVW. Z is some function k UVW. Right? So there's your transformation sequence. In that case, if you do that, you formally had a triple integral over d, f of x, y, z, say dx, dy, dz, right? Now you have a triple integral over g of f of g UVW, h UVW, k UVW. Right, so you have this composition here for those three transformation functions, and then you have times the determinant of j u v w du dv dw, right? And this j here, well, it probably shouldn't come as a lot of surprise. This j of UVW is still a determinant. In particular, it is the following determinant. So j of UVW looks like partial x, partial u, partial y, partial u, partial z, partial u, and right down the line, xv, yv, zv, xw, yw, zw. Right? And this is the three-dimensional, the 3D version of the Jacobian determinant. But again, the algebra gets awfully messy here, so we're not going to do one, but be aware it does exist out there. Okay, so that's it for substitution and multiple integrals.